Sri Sai Ram. Today we are coming to end the chapter Magnetic Effects of Electric Current. It is the sixth session of this chapter and last session of this chapter. Having completed all the teaching, all the portions of this chapter, in this lecture we will emphasize only on problem solving, right? Before going to emphasize on some of the problems which you have in your textbook, we will answer the questions which I have given you in the last home assignment. So let us go and see. What's your first question? What is overload? How does it happen? While we are discussing domestic circuits, we have seen what the overload is, right? Once again go through it and I'll explain it. The current in the circuit depends on the rating of the appliances connected to it, right? In domestic circuit, we have two circuits, right? Two parallel circuits we have. One is high power rating circuit, one is low power rating circuit. What does the high power rating circuit and low power rating circuit does? It drags the current that the appliances need to run. For example, if the heater wants 2000 watts, so how much current does it drag if I pass 200 volt? Power is voltage times current. Now, if it wants 2000 watt, if it runs on 2000 wattage, then how much amperes does it need? 2000 by 200, right? I is equal to P by V. So it comes around 10 amperes. If that appliance which want 10 amperes is connected to 5 ampere circuit, what happens? It wants 10 current, so it kind of drags 10 current out of the thin line of 5 amperes. So it overloads on the 5 ampere wire. That is what it is written. The current in a circuit depends on the rating of the appliance current connected to it. If it wants 10 amperes, so it will be connected to 15 ampere circuit, so that 10 ampere can easily pass through that circuit. But again, the choice of wires depends upon the maximum current estimated to pass through them. So the choice of wires which we are using in the circuits will be depending on the circuits we are connecting. If it is a high power rating circuit, that the wires will be thick so as to pass more current. If the wires are thin, it will be in the 5 ampere circuit. It is designed in such a way. In spite of that, if the total power rating of an appliances exceeds this permitted limit, there is a permitted limit for the appliance, right? As we discussed, for that appliance it needs 10 amperes current. If I connect to 5 ampere current, it is exceeding that limit. 5 ampere is only the limit for that wire, but I connected an appliance that wants 10 amperes. That means it is exceeding the limit of the 5 ampere current. That means I am overloading the wire. So they tend to draw a large current. So when it happens, they will draw a large current, and the wire cannot withhold it. So this is known as overloading. So that answers your first question, right? Now let us go to the second question. Why do we use parallel connection in domestic circuits? We have emphasized on this in the last session. Again, let us explore this. So what happens if we connect series circuit, right? See, this is a live wire. You have an appliance here attached in series. Series means what? End on end connection, right? So one equipment is attached here, another equipment is attached in series to this appliance. For example, this is bulb and this is fan. Now I want to switch on this fan. I don't want the bulb. Can I switch off the bulb and on the fan? If I switch on the bulb here, switch off the bulb here, what happens? It disconnects the circuit there. Can the can the current pass through the fan? No. Wherever you have series connection, every appliance in that circuit are important to complete the connection. Otherwise, the current cannot pass through it. Right? So we use the parallel connection. And there are many more advantages which you have written in this answer. Let us see. Parallel arrangement is used in domestic wiring so as to provide equal amount of energy to all appliances. Take the previous example which I said, here you had a bulb, here you had a fan. So live wire is going. So what happens? Here you have a potential drop, some potential drop, and then here also you have a potential drop. So these two are not having the same potential now. I am not giving the same potential to fan and bulb. So what happens? Unequal distribution of potential. Then if suppose I am only taking here bulb and fan, in our house there are many more appliances. They need more and more what? Current. So if I keeping on dropping the potential, so the appliance which I connected in the last won't get the same amount of potential which the first equipment is getting. Right? So we do not want that. We want to give every appliance equal amount of potential, equal amount of voltage. So we need to establish parallel connection. Thus, every connection is independent. Every connection, if you want the cooler, you can on the cooler and off the fan. If you want the bulb, you can on the bulb and off the cooler. So everything is independent, and what the first point here he is telling is, you need to give what it helps in giving the equal potential difference. That means it is helping in giving the equal voltage to every appliance in the house, so that they can drag current how much they need. Now, moreover, if fault or short circuit occurs in any circuit, it will not result in the disconnection to other circuits. That's what we discussed. If I say every appliance is independent of other, so one usage will not depend on other. If I want to on the fan, I can easily on the fan by switching off any other thing if I don't want that. So no appliance in our house is depend on other appliance. Understood? Now this reduces the equivalent resistance and results in consumption of less energy. That means in power you have already studied. What is power? It is I square R. When the R is more, when the resistance is more, if it is connected in series, what happens? The power lost will be more. The power consumption will be more. Not lost, the power consumption will be more. So what happens? It is not appropriate uses, right? It is not economical. So this parallel connection also reduces your power consumption. You already know the equivalent resistance in series is greater than equivalent resistance in parallel. So when you connect resistance in parallel, your equivalent resistance will drop down, and thus your power consumption also will drop down. Alright, so this answers this question. Now let's go to the third one. Why is it necessary to have earthing for metallic electrical appliances? This is also very important. Why we need earthing? Why we need earth wire? As we discussed in the last session, we spent a lot of time on discussing this. What happens when you don't have an earth wire? If you have a metallic body, what happens? If for suppose live wire is at some current is leaking onto the metallic body from the live wire. By chance you touched it. What happens? The current will flow through you through the earth surface, to the earth's surface. Why it will flow through you, not the neutral wire? Because you provide the low resistance path to the charge. So current always travels through the low resistance path. You are providing that by touching it. So you will get an electrical shock. So in order to prevent that, what we do is we connect the earth wire directly to the metallic appliance, and that metallic appliance is directly connected to the ground. So this is how we prevent from the earthing. Now let us go through the answer. The metallic body of the electrical appliance is connected to the earth by means of earth wire, so that any leakage of electric current is transferred to the ground. Right? If you have any leakage on the metallic appliance, as metallic appliance is the conductor of electricity, you will get a shock. So in order to prevent that, it is it is connecting directly to the ground. It is taking that wire directly to the ground, so that if any excess charge is there, it will directly go inside the earth. As we call, earth is the sink of charges. It will drag any charge if you have in excess. This prevents any electrical shock to the user. Yes, that is why earthing of the electrical appliances is necessary. This is self-explanatory, right? Now let us go to the next question. Why alternating current is useful in power transmission? Why is it useful? While we are studying electromagnetic induction, we have discussed if we change the current, then only the magnetic field can change. Right? How the current will be induced in the secondary coil due to the primary coil? When the current in the primary coil is alternating, that means it is changing its direction. That means what? I am changing the magnetic field also. That change in magnetic field in the secondary coil will cause an induced current. That we call as what? EMF. The potential difference that is created in the secondary coil due to the primary coil we call as EMF. So for suppose if in transformer, in the primary coil we pass direct current, what happens? Direct current is unidirectional. It does not reverse. It does not reverse its direction every now and then. So there is no change in electric current. When there is no change in electric current, will there be any change in magnetic field around it? No. But the point to be noted is, in the secondary coil, the current is induced due to the change in magnetic field, not due to the magnetic field. If there is a change in magnetic field, then only current will be induced. So alternating current will facilitate us to change the magnetic field in the primary coil. That will induce the current in the secondary coil. This whole process we call as electromagnetic induction. So that won't be useful if you pass direct current through it. Right? From the primary coil you have, for suppose in the example in the last class, we saw that 1000 volts are coming. I need to step it down to 200 volts. Right? The voltage needs to be altered. The current needs to be altered. Now, if I have to induce in the secondary coil, I need a change in magnetic field in the primary coil, and in that vicinity the secondary coil is also there, so that this change in magnetic field will also happen in the secondary coil, near the secondary coil. So the current will induce there. So that is what in short the answer is written. A major advantage of alternating current is that its voltage can be modified relatively easily using transformer. Right? In transformer what? Transformer works on electromagnetic induction. If anything has to work on electromagnetic induction, it needs to alter the magnetic field. When we can alter the magnetic field? If you have the variable current. So alternating current is useful in the transformer. So which allows power to be transmitted at very high voltages before being taken down to the safer voltages for the commercial and residential use. What it is telling is, to drop down the voltage, to make the current high, we need what? A step down transformer, step up transformer. Step down transformer from the station to our house. So in that we need to have this manipulation of high voltage to low voltage, relatively low voltage, and low current to relatively high current. So this alternating current will be useful in the power transmission. Okay, that's what it is written in the answer. So this answers all your questions in your home assignment. Now we only will discuss on some questions in your exercise. I took 3 questions. All the other questions are straightforward, which you already discussed in the class, and the notes for each and every questions will be given to you. Now we will discuss only the 3 questions in the exercise which are a bit tricky. Right? Let us go and explore them. So this question is from in your text 13.7. You can see in your page 238. So the question here is, an electrical oven, it has a power rating of 2 kilowatt. Rating is operated in domestic electrical circuit. How much voltage we are getting in domestic electrical circuit? 220 volts. That has a rating of 5 amperes. So to that circuit we are attaching 5 ampere current line. Okay. So what result do you expect? Explain. Before answering this question, just see the appliance. It is an electrical oven and we are supplying 220 volts. So what will be the current it needs to draw? So what power is equal to? Voltage times current. So current will be the power divided by this voltage. Right? That much current we need now. So 2000 divided by how much voltage? 220. So it comes near 9 amperes. Right? 2000 by 220 comes 9 point something it comes. And it needs 9 amperes now. And in what line we have connected it? In what current rating line we have connected it? We have connected it in 5 ampere line. It needs 9 ampere, but we connected in a line of current that can hold a maximum up to 5 ampere. What result do you expect? Is it not overloading? That's what the answer is. Let's see. The current drawn by the electrical oven can be calculated using the formula as we discussed. Power is voltage times current. So to calculate current, what? Power by voltage, using mathematical equation you can easily see this. So substituting the values, we get current is equal to 2000 watts he gave, and 220 volts we are supplying. So current it needs is 9.09 amperes. But the wire we have, it can hold only 5 amperes. So what happens? It heats up quickly and it melts. This is what we call as overloading. The current drawn by the oven is 9.9, which exceeds the safe limit of 5.5 amperes of the circuit. This causes the fuse to melt and break the circuit, right? If you have more load, what happens? It cannot hold, and if you have this much amount of a huge crowd is coming, huge crowd of charges are coming, so the atoms get collided. When you collide electrons with atoms, so what happens? Heat dissipates, heat comes, heat produces. When you have the heat, the wire melts. So this is what happens in this question. Now, next question. This is from your exercise, 8th question of your exercise. How does a solenoid behave like a magnet? Can you determine the north and south poles of a current carrying solenoid with the help of a bar magnet? Explain. Solenoid is what? Group of circular coils, right? It is spiral coil we have. So when you when you pass a current through it, what happens? You studied already, when a current carrying conductor will have a magnetic field around it. So when you have a magnetic field around a current carrying conductor, and you already saw the circular coil, so inside that coil you will see every part of the coil will contribute to a current inside in the same direction. So group of coils, when you pass a current, what happens? You will have a uniform magnetic field inside the solenoid where you pass the current. So outside also you will see a pattern of magnetic field lines, right? If you take a bar magnet and put near it, he is asking, can you determine which pole is having on which side? So let us go and explore. Let us see what the solenoid is. A solenoid is a long coil of circular loops of insulated copper wire. Okay, on the upper part of it you have insulated copper wire. By chance if anybody touches it, you will not get a shock. So that is the safety precaution. So the magnetic field produced around the solenoid when the current is passed through it is similar to the magnetic field produced around the bar magnet when current is passed through it. And we are claiming it, right? So how? Let us see. So this is a solenoid, right? This is the positive terminal, this is the negative terminal. We are passing the current, the charges are going from here. Actually electrons goes from here. Conventional current, what we say, from positive it goes to negative. Now using right hand thumb rule, what happens? See this segment, curl your finger, what is the direction of magnetic field? Inside. So every coil will contribute the same magnetic field inside the solenoid, and uniform because these are of same radius. So every magnetic field inside the solenoid will be uniform. And does it not seem like a bar magnet? One end it is a north pole, one end it is south pole. What are the properties of magnetic field lines? It comes from the north pole and goes to the south pole. That's what exactly it is doing. Now our task is to see which end is north pole, which end is south pole. By definition we know like poles repel and unlike poles attract. Just put a bar magnet near any end of this. If it feels a repulsion force, and we know, having known the which end of the bar magnet is north and which end of the bar magnet is south, we can determine which end here is north. For example, this is a bar magnet. This is the north pole and this is the south pole. If I put my north pole here, what will it experience? It will experience a repulsion force. If it experiences a repulsion force, what can I intuitively think? This end of the solenoid is a north pole. Right? That's what we explained here. When the north pole of a bar magnet is brought close to the end connected to the negative terminal of the battery, the solenoid repels the bar magnet. Right? The solenoid repels the bar magnet. So when it repels the bar magnet, what we conclude? The other end is also the same pole. Then only we can repel. So like poles repel each other, we can infer that the end is connected to the negative terminal behaves as a north pole. So end connected to the negative terminal behaves as a north pole. We concluded from this. So while the end, so if this becomes north pole, the other end automatically becomes a south pole, right? So this is how we determined which end of a solenoid is north pole and which end is south pole. So this is how the question goes, answer goes. Now let us go to the last question. Imagine that you are sitting in a chamber with your back to the wall. An electron beam is moving horizontally from the back wall towards the front wall, is deflected by a strong magnetic field to your right side. What will be the direction of the magnetic field? This is the back wall. This is the front wall. The electron beam is going in this direction. The force experienced by the electron towards my right, right? That means this is the force direction. Okay. Now he is asking what is the direction of the magnetic field. You already know the motion of electrons is in the direction opposite to the motion of current. If the electron is moving from back wall to front wall, what will be the direction of the current? It will be just opposite to it, right? The current direction will be like this. Using Fleming's left hand rule, you can easily tell what will be the direction of the magnetic field which he is asking. So this is the thumb gives you direction of force. Forefinger gives you direction of magnetic field. This gives you direction of current. Now he gave you direction of force in this direction. Now the current direction is down. What will be the direction of the electron? See once again, the force will be in your right direction. The force will be in your right direction. The direction of the current will be downwards direction. Right, this is direction of current, this is the force. So magnetic field will be inside the board, into the board. Do you understand? Once again I am telling, it is deflected in the right direction. Use your thumb. This is your right direction. Now induced current is opposite to the direction of the electrons. So electron is going from back wall to front wall. So it is for us it is moving up. So the direction of current will be opposite, so it will be down, right? So current direction is down and the force is in right direction, so this gives inside the board. So the magnetic field is inside the board. The magnetic field produced is inside the board. The direction of the magnetic field is inside the board. Let us see how it got explained. The direction of the magnetic field can be determined using left hand rule. The direction of the current is from the wall to the back wall because negatively charged electrons move from the back wall to front wall, right? From back wall to front wall the electron is moving, so the current will be moving from front wall to back wall. The direction of the magnetic force is rightward, as we saw it is on the right. So using left hand rule it can be concluded that direction of the magnetic field is inside the chamber downward. Okay. Now here in our case we studied inward, but it is more or less the same. When does an electric short circuit occur? We studied in the overloading part that short circuit is one of the type of overloading, right? Because when neutral wire and live wire, by mistake if it gets mixed, due to overloading also it melts and gets mixed. What happens? Current goes through that low resistance path, so wire offers very low resistance, so hundreds of amps will generate in short span of time. So how the electric circuit will occur, how many ways it occurs, let us see. So there are two ways. First one is when two many appliances are connected to a single socket, or when high power rating appliances are connected to a light circuit. The resistance of the circuits becomes low as the current flowing through the circuit becomes very high. This condition results in short circuit. What he is telling is, if you have one socket and you use an extension box, for example that socket only is designed to draw 5 amperes and you plug the extension box, and to the extension box you connected 5 more devices. That is only designed to draw 5 amperes, but by connecting all these devices you are demanding how much, or 10 or 12 amperes. So it is exceeding. So when it is exceeding, what happens? It becomes low resistant because the potential difference is constant, right? Current flow will be more, it melts. So that is also one of the type of short circuiting. This is one of the way. And also he told that when you attach large high power rating appliance in the light power circuit. In the light circuit, that means 15A rating appliance, if you attach to 5A circuit, what happens? It also melts. So this is one of the type. What is the second type? When a live wire whose insulation have worn off come in contact with each other, the current flowing in the circuit increases abruptly, which result in short circuit. So you have insulation, right? For the live wire and neutral wire, you have red wire and you have black wire. So if the insulation melts, what happens? The two wires get contact with each other. The same thing happens again. Again, current takes the path of low resistance. Immediately, abruptly, current will increase because the resistance will be so low and you are providing 220 volts. So current increases. That also results in short circuiting. So these are the questions we discussed today. These are some of the tricky questions. All the other questions which you have in your textbook, we have been covered somewhere or other during the lectures. But every answer to the question we will be giving in the description of this video. Please go through that and go through every topic from where we began and from where we end. We began with current carrying conductor producing a magnetic field, and we studied about the force around the current carrying conductor and application electric motor, and then we studied about the scientist Michael Faraday, and then we explored electromagnetic induction. Then we came to that application we studied in electrical generator. Then we studied about the domestic circuits. So these are all we covered in this. Hope we enjoyed this chapter. Sai Ram.